Now, when we are in an accelerating reference frame, that's what we call a non-inertial reference frame, we will see that if you have an object that is not tightly bound to this reference frame, when the reference frame is accelerating in one direction, there will be an apparent force that will act on the object in the opposite direction. These forces are called fictitious forces. So they act opposite in direction to the acceleration of the non-inertial frame. So here's an example. A ball on the floor of an accelerating train. So here we have a train that is accelerating to the right, and we have a ball here on the floor of one of the cars, and this ball is not tightly fastened to this floor. Therefore, when the train starts accelerating to the right, the ball starts accelerating to the left with respect to the train. And why? Because there is a fictitious force F that is acting to the left, which is equal to mass times the acceleration of the train. Another example is centrifugal force in a car rotating around a circle. So when we have a car rotating in a circle, we must have a centripetal force which is responsible for the centripetal acceleration. And because this is a non-inertial reference frame, it's an accelerating reference frame. If you have an object inside this car that is not fastened tightly to this to the floor of this car, you will see that this object will feel a ghost force or fictitious force, which we call centrifugal force if this is a rotating reference frame. And the centripetal force was in minus r hat direction, which was responsible for the acceleration of this reference frame, centripetal acceleration. The object that is not fastened tightly to the accelerating reference frame feels the ghost force, that's called the centrifugal force in plus r hat direction in this case. Now, another example would be the Coriolis force. So the Coriolis force appears in changing the radial position of an object in a rotating system. So you have a rotating system, therefore you have the centrifugal force, plus you're changing the radial position of this object, and you will see that there's going to be the Coriolis force appearing on this object. Okay, so now, when we have an accelerating reference frame with respect to a reference frame at rest, for example, this is the Earth reference frame, this is the accelerating reference frame, remember that when these two reference frames are trying to report the position of a point, the reference frame at rest, the inertial reference frame, reports r for the position vector. The reference frame that is accelerating reports r prime, and at t equals to 0, if the origins would overlap, we would have a separation of 1/2 as prime t square between the two origins at time t. So you can see that the position vector r is the position vector reported by the s prime reference frame plus 1/2 as prime t squared. The velocity is as prime t plus v prime. Acceleration is as prime plus a prime. So a prime, the acceleration reported by this reference frame, is equal to the acceleration reported by the s reference frame minus the acceleration of the s prime reference frame with respect to s. So if the acceleration is 0 in the s reference frame, you will see that the acceleration reported by the s prime reference frame would be minus as prime. So as prime is the acceleration with respect to s. Because this is a non-inertial reference frame, the observer in this reference frame reports a minus as prime, which is due to a fictitious force minus mas prime appearing on this object with mass m. Okay. So we can basically see this fictitious force comes right out of Galilean transformation for a non-inertial, inertial to non-inertial reference frame. Now, let's take a look at this example. A person weighs a fish of mass m on a spring scale attached to the ceiling of an elevator as illustrated in figure. So this fish is attached to this spring scale. This person is inside the elevator. If the elevator accelerates up, the person will be, or down, the person will be in a non-inertial reference frame. So when the acceleration of this reference frame with respect to Earth reference frame is up, there will be a fictitious force pointing down, mass of the fish times acceleration A. If the elevator accelerates down, there will be a fictitious force acting on it, mass times acceleration, in the upward direction. And we have the tension that is being measured by the spring scale, and mg, the weight of the fish, pointing down. So show that if the elevator accelerates either upward or downward, the spring scale gives a reading that is different from the weight of the fish. Evaluate the scale readings for a 40 Newton fish, that's the weight of the fish, if the elevator moves with an acceleration upward or downward 2 meters per second square. Now, when we look at the free body diagram for the fish, there is the tension pointing up, there is the weight, and we have two scenarios. When the elevator is accelerating upward, we have a fictitious force, mass of the fish times acceleration of the elevator, pointing down. If the acceleration of the elevator is down, the fictitious force points up. And we are looking at this from the point of view of this non-inertial observer who is in the accelerated reference frame. Now the net force on the y-axis, so this is our y-axis, and the net force on the y-axis must be equal to 0 because the fish is not moving with respect to the non-inertial observer. So the tension is pointing up. Now if we're looking at the scenario where the elevator accelerates upward, the fictitious force points down minus mass of the fish times acceleration of the elevator. This must be equal to mass of the fish times g. And if the acceleration is downward, then we would have the force in the same direction, fictitious force in the same direction as tension force. This must be balancing mg. So when the acceleration of the elevator is upward, our reading for the tension is mg plus ma, mass times acceleration of the elevator. If the acceleration of the elevator is downward, our reading is mg minus ma, acceleration of the elevator. So you can see that we have shown the true weight of the fish is mg, but the reading that we have for upward acceleration is greater than the true weight. For downward acceleration, it's less than the true weight of the fish. So this is part A of the problem. Now, we can also look at this from the inertial observer, the Earth observer point of view. So this would be an observer over here watching this experiment. Now, for this observer, we would have a free body diagram that will only contain the real forces, tension and mg. So we have tension and mg pointing down. This is the y-axis. Now the net force on the y-axis is the tension minus mg, and if the acceleration of the elevator is up, this would be equal to mass times acceleration of the elevator. If the acceleration of the elevator is pointing down, then this would be equal to minus m times acceleration. Because in the first scenario where we have A pointing up, the net force on the y-axis would give us ma, and when A is pointing down, the net force would be minus ma. Okay, so in this case, basically we find that tension is again mg plus ma when it's accelerating upward, and it is mg minus ma when it is accelerating downward. So this is accelerating up, that is accelerating down. So for part B, we want to evaluate these numbers. Now, if the acceleration in the upward direction is plus 2 meters per second square, the tension would be 40 plus the mass of the fish, 40 divided by 9.8 meters per second square times 2. That would give us 40 plus 8.2, 48.2 newtons. If the acceleration of the elevator is downward, in the downward direction, 2 meters per second square, the tension would be 40 minus 40 divided by 9.8 times 2. This is now 40 minus 8.2, which is 31.8 newtons. So due to the fictitious force that appears in the non-inertial reference frame, which is the elevator reference frame, we have a reading that is different from 40 newtons. When it is accelerating upward, it's 48.2. When it is accelerating downward, it's 31.8 newtons in the reading in the spring scale. Okay, another example. A car accelerates down a hill going from rest to 30 meters per second in 6 seconds. A toy inside the car hangs by a string from the car's ceiling. The ball in the figure represents the toy of mass 0.1 kilograms. The acceleration is such that the string remains perpendicular to the ceiling. Determine the angle theta and tension in the string. So we have to draw a free body diagram for the toy. This is x-axis, this is y-axis. There will be a weight of the toy that is pointing down. So this is going to be mg pointing down. There is the tension in the string. And because we are in an accelerating reference frame, the acceleration is downward. There will be an acceleration in the upward direction, the fictitious force in the upward direction. So you can see that I have the tension making an angle theta with respect to the vertical, mg, and I also have the fictitious force making an angle theta with the horizontal that is opposing the acceleration of the car. So the car is accelerating in the downward direction. Okay, and it's not moving. So the net force on the y-axis should be equal to 0. So that means I should have t cosine theta in j-hat direction, fictitious force sine theta, ma sine theta in j-hat direction, minus mg equals to 0. Net force on the x-axis must be equal to 0. Tension component t sine theta on the x-axis, so that is in minus I-hat direction. The fictitious force has a positive component, ma cosine theta I-hat, so this must be equal to 0. So this gives us tension equaling ma cosine theta divided by sine theta. So we have, if we substitute this result into the first equation, we would obtain for t cosine theta, ma cosine square theta divided by sine theta plus ma sine theta equals to mg, which is ma parentheses cosine squared theta plus sine squared theta divided by sine theta equals mg. So you can see that the m's will cancel here, and we're going to substitute for cosine square plus sine square 1, and therefore we find that the acceleration a is equal to g sine theta. So m's will cancel here, and we're going to have a times 1 divided by sine theta equals g, which gives us a is equal to g sine theta. Or we can find the angle as theta equals sine inverse of a divided by g. Now also we have the acceleration of the car, that is dv dt. We go from rest to 30 meters per second in 6 seconds. So delta v divided by delta t in this case, it's 30 divided by 6 is 5 meters per second square. So we find that the angle theta should be sine inverse 5 divided by 9.8 meters per second square, which gives us an angle of 30.7 degrees. Okay, and the next question is the tension in the string. So the tension in the string is basically ma cosine theta over sine theta, or tension is ma cotangent theta. And we can evaluate cotangent of this angle. So the mass of the toy was given as 0.1 kilograms. So it's 0.1 kilograms. The acceleration is 5 meters per second square times cotangent of 30.7 degrees. This gives us a tension of 0.843 newtons. Okay, now alternative solution. Alternatively, if you don't want to deal with fictitious forces, then you have to use an inertial observer. So inertial observer would be an observer at rest outside. This is the inertial observer looking at this car. This inertial observer sees that there are two real forces acting on this toy. There's the tension and making an angle theta with the vertical mg. So it's the same free body diagram, except the fictitious force changes, plus the effect is to have an acceleration in the Earth reference frame pointing an angle theta with respect to the horizontal in the downward direction. Okay, so for this case I would write net force on the x-axis would be basically minus t sine theta, and because this toy is accelerating downward in the Earth reference frame, this would be equal to minus ma cosine theta, and the net force on the y-axis is t cosine theta minus mg. There is an acceleration component on the y-axis, which is minus ma sine theta. So you can see that I obtained the same equations from this free body diagram. So if you're using an inertial reference frame, you can only use real forces, no fictitious forces, but then you have to take into account that the inertial reference frame observer sees the system as a whole, while the ball is not moving with respect to the non-inertial observer inside the car. It is moving according to the Earth observer because it's moving together with the car with the acceleration pointing down. So this has to be taken into account. Let's move on to another example. Now we have a car and there's an object inside with mass m. The car is accelerating with 8 meters per second square. Coefficient of kinetic friction between the object and the floor of the car is 1.2, and the distance between two ends is 6 meters, and this object travels from the right hand side to the left hand side. Because the acceleration is to the right, it's going to feel a fictitious force to the left, and it will go and hit the other end. So how long does it take to reach the other end? Okay, so again, I'm going to solve this from two different points of view. This is my inertial observer outside, Earth observer, watching the car and the object. So this observer notices that there is a normal force acting on this object because there's a contact between the floor of the car and this object. There is mg, the weight. Because this object is moving to the left, there must be kinetic friction pointing to the right. And those are only three real forces acting on this object. The net force on the y-axis must be equal to 0 because according to my inertial observer, it's not moving on the y-axis. So normal force minus mg must be equal to 0. Therefore, the normal force is equal to mg. The net force on the x-axis must be equal to mass of the object times acceleration measured by the inertial observer. Now, the net force on the x-axis is the kinetic friction, which is mu k times the normal force. So it is mu k times mg, which is mass times acceleration reported by the inertial observer. The m's will cancel, so I find that the acceleration reported by the inertial observer is mu k times g, or g divided by 2. So this is the acceleration. Now, with this acceleration, we have a displacement. So how much is our displacement in time t? Delta x. So this displacement is, when you go from time t equals 0 to t, the car is traveling with a constant acceleration, so 1 over 2 at squared displacement from the car, and the object is moving inside the car a distance d, which is 6 meters. So this is the total displacement of the object in the Earth reference frame, and it's performing a constant acceleration motion with acceleration g over 2. So this must be equal to 1 over 2 at squared because it's constant acceleration motion. And therefore, we see that 1 over 2 t squared parentheses capital A minus A is equal to d. So then we find that the time it takes to complete the motion is square root 2d. So this is our inertial observer acceleration, 2d divided by capital A minus acceleration reported by the inertial observer. So if we plug in the numbers here, square root 2 times 6 meters divided by 8, 9.8 divided by 2 is 4.9. So we find roughly 1.97 seconds as the answer to complete this motion. Now, alternative solution, non-inertial reference frame. Who is the non-inertial observer? The person inside the car is the non-inertial observer. The non-inertial observer reports a normal force pointing up, mg pointing down. According to this observer, the object is moving to the left, so kinetic friction pointing to the right. Because we are in an accelerated reference frame, there is a fictitious force m times capital A pointing to the left because acceleration is to the right. Now, according to this observer, net force on the y-axis is again 0 because the object is not moving on the y-axis. According to this observer, the net force on the x-axis is the kinetic friction minus the fictitious force, which is mu k mg minus ma the fictitious force. This is mass times the acceleration reported by the non-inertial observer. So what is this acceleration reported by the non-inertial observer? Well, acceleration, because masses will cancel here, we will find that the acceleration reported by the non-inertial observer can be written as mu k times g minus capital A. So this is 4.9 minus 8 meters per second square minus 3.1 meters per second square. So with this acceleration, we have a displacement delta x equals d, which is 1 over 2 acceleration reported by non-inertial observer t square. Therefore, we find that t is square root 2 times 6 divided by 3.1, which is the same answer, 1.97 seconds. So whether we solve it with inertial reference frame or non-inertial reference frame, we should obtain the same result. The only difference between the two is we talk about real forces in the inertial reference frame and fictitious forces in the non-inertial reference frame, mass times the acceleration of the reference frame, pointing opposite to the acceleration of the reference frame. And in this reference frame, non-inertial reference frame, the displacement is d. In the inertial reference frame, the displacement is 1/2 at squared minus d, because the car is moving to the right. So this basically completes the solution for this problem. Let's move on to another example. A student, along with her backpack on the floor next to her, are in an elevator that is accelerating upward with acceleration a. The student gives her backpack a quick kick at t equals 0, imparting to its speed v and causing it to slide across the elevator floor. At time t, the backpack hits the opposite wall, a distance L away from the student. Find the coefficient of kinetic friction between the backpack and the elevator floor. So this travels a distance L to the other side, and we want to know the coefficient of kinetic friction. So let's solve it from non-inertial observer point of view. Non-inertial observer is the student. So the student is in an accelerating reference frame. The student reports a normal force acting on this object, the weight mg pointing down. Because it's moving to the right, there must be a kinetic friction towards the left, and because it's accelerating up, mass times acceleration pointing down, fictitious force. So according to the student, there is no motion on the y-axis. Net force on y is 0. Therefore, normal force minus mg minus ma, fictitious force, is equal to 0. So the normal force is m times g plus a. The net force on the x-axis is just kinetic friction minus Fk, that is equal to that's equal to mass times acceleration on the x-axis, because it's actually decelerating. So it starts with a speed v and stops on the other side. That means it's decelerating. So the acceleration will be negative. So this is going to give us minus mu k times the normal force minus mu k m g plus a is equal to mass times the acceleration. The m's cancel, and we find that the acceleration is deceleration. So it is minus mu k g plus a. So it's decelerating. The distance we travel, delta x, is L. So the backpack travels a distance L. So starting with at t equals to 0 a speed v and performing constant acceleration motion, we have the distance traveled equals v times t minus 1 over 2 ax t squared. So actually it's plus, but because we have an acceleration that is negative here, so this would become minus. So we have 2L, 2 times L minus Vt is equal to minus mu k g plus a t square. And on the other hand, the acceleration on the y-axis is 0. So we can see from here that mu k can be found as 2 Vt minus L divided by g plus a t square. So v is known. It's the initial speed we give to the backpack. Distance L is known. G plus a is the acceleration of the elevator that's pointing up. And time t, the backpack hits the opposite wall, so t is known. So we have calculated mu k in terms of the known quantities. Now, alternative solution, inertial observer reference frame. Inertial observer is the person on Earth watching this experiment. Only real forces. So we don't have the fictitious force. We have mg, n, and fk pointing to the left. The net force on the y-axis, however, changes. This is n minus mg, and because the backpack is a part of the elevator which is accelerating up, it has a net force ma pointing up. It is accelerating with the elevator. So we have to take that into account, and the normal force is once again m times g plus a. The net force on the x-axis is minus fk, which is minus mu k m g plus a, which is mass times the acceleration. So these two masses cancel, and I find that inertial observer and non-inertial observer report the same x component of acceleration but different y component of acceleration. So this observer says it's 0, this observer says it's a. Okay, and the distance traveled, they also measure the same delta x. Why? Because the acceleration is on the y-axis. So delta x, the distance traveled L, is equal to, starting from speed v, vt, plus 1 over 2 ax t square, where ax is minus mu k g plus a. It is vt minus 1 over 2 mu k g plus a t squared. That is L. So we get the same answer. Mu k must be equal to 2 times Vt minus L divided by g plus a t squared. Okay. So we have solved it from the student point of view, where we have the fictitious force pointing down because the reference frame is accelerating up, and we have solved it from the Earth reference frame point of view. This difference between these two observers is not affecting the acceleration on the x-axis and the distance traveled on the x-axis. It only affects the interpretation of the motion on the y-axis. The non-inertial observer says there is no acceleration up. The inertial observer says there is an acceleration up. So this object is accelerating together with the elevator. Okay, so one last example. A magician pulls a tablecloth from under a 200 grams mug located 30 centimeters from the edge of the cloth. The cloth exerts a friction force of 0.1 newtons on the mug, and the cloth is pulled with a constant acceleration of 3 meters per second square. How far does the mug move relative to the horizontal tabletop before the cloth is completely out from under it? Note that the cloth must move more than 30 centimeters relative to the tabletop during this process. Now, I start with a free body diagram of the mug. So here is my mug. It feels a normal force pointing up, mg weight pointing down. Now this cloth is being pulled to the right. That means the cloth feels a friction to the left, so the mug feels a friction to the right. So the kinetic friction is acting to the right on the mug. Okay, so this is an important observation because it's a mutual force between the mug and the cloth. The friction on the cloth is opposing its motion, so the friction on the cloth pulled out is to the left, and on the mug to the right. Newton's third law, action reaction. Okay, the net force on the y-axis is the normal force minus mg, and there's no motion on the y-axis, so normal force is equal to mg. The net force on the x-axis is the kinetic friction, which is mu k times the normal force. Normal force is mg, so it's mu k times mg, which is 0.1 newtons. It's given in the problem statement, and this is mass times acceleration, and basically the mass of the mug was 200 grams, so it is 0.2 kilograms, 0.2 times the acceleration. So the acceleration here is the acceleration reported by the inertial observer, and the acceleration reported by the inertial observer is 0.1 divided by 0.2, 0.5 meters per second square. So now I want to think carefully about the inertial observer and non-inertial observer. So who is the non-inertial observer? Non-inertial observer would be sitting on this cloth. So that is our non-inertial observer in the accelerated reference frame. So I remind myself what happens if this cloth accelerates with respect to the tabletop. So this is the reference frame of the cloth. This is the reference frame of the tabletop, and the cloth was accelerating with acceleration 3 meters per second square to the right. So this is accelerating 3 meters per second square to the right, and a position vector reported by the inertial observer is related to the position vector reported by the non-inertial observer, our non-inertial observer, by adding a vector with magnitude 1 over 2 3t squared. So the position reported by the inertial observer is position reported by non-inertial observer plus 1 over 2 3t squared in I-hat direction. Acceleration reported by inertial observer is acceleration reported by non-inertial observer plus 3 I-hat, because I have to take two derivatives. So this gives me acceleration reported by non-inertial observer to be acceleration reported by inertial observer minus 3 I-hat. This was 0.5 I-hat minus 3 I-hat. So acceleration with respect to the cloth, acceleration reported by non-inertial observer, acceleration with respect to the cloth reference frame is minus 2.5 I hat meters per second square. And how much does the mug move relative to the cloth? We know that the mug moves 30 centimeters to the left with respect to the cloth, because the cloth is pulled out 30 centimeters. The mug is moving to the left 30 centimeters. The displacement of the mug, as reported by the cloth observer, is 1 over is basically 30 centimeters, and it's in the minus I hat direction, minus 30 centimeters. We have an acceleration in the minus I hat direction, so it is minus 1 over 2, 2.5 t square. So we find that t square is equal to 60 divided by 2.5. Now, how much does it move according to the inertial observer? This is going to be 1 over 2 acceleration reported by inertial observer t square, which is 1 over 2, 0.5, 60 divided by 2.5 is t square, which gives us 6.00 centimeters. Okay, so the distance traveled by the mug with respect to the tabletop. It is to the right for an amount of 6 centimeters. Okay. Now, if I solve the same problem alternatively using a non-inertial observer free body diagram, that's the cloth reference frame, I would have to draw the normal force acting on the mug, the weight, the kinetic friction pointing to the right. Those were the real forces. Now the cloth is accelerating to the right. That means I have a fictitious force to the left, mass times acceleration of the cloth. The net force on the y-axis must be equal to 0, so the normal force is equal to mg. The net force on the x-axis is the kinetic friction minus the fictitious force, mass times acceleration of the cloth, is mass times acceleration reported by the non-inertial observer. The kinetic friction was 0.1 newtons, mass of the mug is 200 grams, the acceleration of the cloth is 3 meters per second squared. This is 0.2 times acceleration reported by non-inertial observer, and acceleration reported by non-inertial observer is minus 2.5 meters per second square. So I have same result obtained using this alternative approach. So in this case, we have seen that this when this cloth is pulled out, there is the friction acting on the cloth to the left must be pointing to the right on the mug. So this was our first important observation. Then we have to draw the free body diagram. We have two choices: use the inertial or non-inertial observer. The inertial observer only has the real forces, normal force up, mg down, the friction force to the right, and that means we can use net force on the x-axis Fk, which is given in the problem as 0.1 newtons, mass times acceleration reported by the inertial observer. There is a net acceleration 0.5 meters per second square in the I hat direction. And then we have looked at Galilean transformation, which tells us that the acceleration reported by the cloth observer is actually acceleration reported on the tabletop minus the acceleration of the cloth with respect to the tabletop, so minus 2.5 I hat meters per second square. Later on, using the free body diagram with respect to non-inertial observer, taking into account a fictitious force mass times acceleration of the cloth to the left, we see that it's the same acceleration that we find. And the mug moves 30 centimeters to the left with respect to the cloth here. So with respect to the cloth, because the cloth is pulled out 30 centimeters. The 30 centimeters is 1 over 2 acceleration in the non-inertial reference frame t squared. That is t squared 60 over 2.5. The distance traveled in the inertial reference frame is 1 over 2 acceleration in the inertial reference frame t squared 1 over 2 0.5 60 divided by 2.5, that gives us 6 centimeters. That is the distance traveled by the mug with respect to the tabletop. Okay, alternative solution, as we have seen, gives us the same value of non-inertial observer acceleration using the fictitious force. Now there is a statement here about the cloth must move more than 30 centimeters relative to the tabletop during this process. That is correct. So because the cloth has to be completely out, because the mug will move 30 centimeters from the edge of the cloth. So this must be the case for this experiment to work.